look at this thing. It's ridiculous. I mean, have you ever seen anything like that before in your life? Because I definitely haven't. So for those of you who are new here, we do Space is Weird on this channel, and weird is a good thing. And this week's weird thing is IC418, also known as the Spirograph Nebula. For those of you who remember that toy when you were a kid, Spirograph, that used to make those really cool shapes with those cogs that you would put your pen in and wind all the way around. And you can probably see why it's called that. It has a very striking similarity to Spirograph. And I actually learned that the official term for those shapes is a hypotrochoid and an epitrochoid. A hypotrochoid is when you put your cog inside the circle and move the pen around, and an epitrochoid is when you put your cog and your pen outside the circle and work your way around it. See, you learn something new every day. So IC418 is what we call a planetary nebula. It's about 3,600 light years away from Earth in the direction of the constellation of Lepus, which is just underneath, or at least underneath from the northern hemisphere, Orion. If you're in the southern hemisphere, it'll just be above Orion. And it's about 0.3 light years across. It's something in our own Milky Way galaxy. And even though it's called a planetary nebula, it has absolutely nothing to do with planets. It's a historical term that was coined when people didn't really understand what these things actually were. They were round and fuzzy in the sky, so they were dubbed planetary nebula because, well, planets are round, and nebula were all of the fuzzy things in the sky that didn't look like stars. Nebula is Latin, meaning sort of like a cloud or a fog. And the name is still used today, even though we now know better, and we know that these planetary nebula are actually the remnants of stars that have ended their lives. Now, these aren't supernova remnants. A supernova is when a truly massive star, so something like 20 to 100 times the mass of the sun, runs out of fuel, collapses in on itself, and then bounces back in an explosion or a supernova. Instead, planetary nebula are the remnants of stars that are very much like the sun. So everywhere from sort of the mass of the sun to about 8 times the mass of the sun. When these stars run out of fuel, first of all, they swell up to these big red giant stars, and we think the sun will do that one day, maybe even swelling up to sort of go past the orbit of Mars. Essentially what the star does when it runs out of hydrogen to burn like it normally does with nuclear fusion, like the sun is doing all the time, is that it poofs out those outer layers into this red giant star as it starts to burn helium in its core instead. When it starts to run out of all of that, then it can't hold on to those outer layers anymore, and they sort of just get poofed out into space, and you're left with these beautifully round planetary nebula. And what you're left behind with in the middle is a white dwarf star, which is sort of like the old core of the star where it used to be doing all of that nuclear fusion, but now it's just this sort of pile of inert helium. As I said, this is the eventual fate of the sun, but not for another 5 billion years or so. We're actually really lucky to be able to see these beautiful planetary nebulae because they don't actually last for very long. They're only around for about 10,000 years or so.
10,000 years will give you such a crick in the neck.
Now that might sound like a long time to me and you, but astronomically it's like the blink of an eye, you know, compared to the sun's 10 billion year lifetime. And so what these planetary nebulae are made of is just this really underdense gas that has just been poofed off into the surrounding space. So it's amazing that we can even see that gas because, well, we look around us right now, we can't see the air in front of us. And so the only reason we're actually able to see these planetary nebulae is because the gas in them is ionized and it's glowing. So what does that mean? So what's happening is that white dwarf core that's left behind after this planetary nebula is formed is actually still giving off a lot of energy. It's still radiating a lot of light, in particular UV light. And so that UV radiation actually impacts that gas that's surrounding it. So it'll mostly be hydrogen, but there'll be some helium around there as well, maybe a little bit of oxygen and nitrogen sprinkled in as well. And what that UV radiation does is give the electrons in those atoms enough energy to escape the atom. And that's what we mean by ionized. We mean that the atoms are no longer neutral. They'll have a positive charge because they've lost one of their electrons that's now free to roam space. So for example, if an oxygen atom has one electron missing, that's called an oxygen ion, and it'll be written O plus to show that it has a positive charge. Although that's not the notation that astronomers use. We would call that O and then 2 Roman numerals, because O and 1 Roman numeral would clearly be neutral oxygen, and O with 2 Roman numerals means that 1 electron is missing. It's incredibly confusing, but again, historic notation, and we stick with it. Now, if you have ionized gas like that at very low densities, like you have in a planetary nebula, then the UV radiation still coming from that white dwarf core will actually be able to cause the remaining electrons in the atoms, of course, one of them to jump up an energy level. If you remember chemistry at high school where you had sort of the levels of electrons around atoms, it can jump up to one of those. But it's not supposed to be there, so it actually ends up dropping back down again to where it's supposed to be. And in that process, it gives out light. Now, because those electron levels are separated by exactly the same amount of energy every single time, according to, quantum mechanics that, governs atoms, the same amount of energy will always be released. And what's released is a photon. And a photon with the same amount of energy will be a specific color or wavelength every single time. In a normal density gas, all those ionized atoms would actually collide, and that would actually prevent those electrons from jumping up and jumping back down. So we actually call this emission of photons from this ionized gas forbidden emission, or actually forbidden lines, because what you see if you split the light from the planetary nebula up into all of its component wavelengths is that you see these huge big peaks of these emission lines at these certain colors or wavelengths that correspond to hydrogen and oxygen and nitrogen that's been ionized. This is actually how we get color in space images. So for example, this image was taken with the Hubble Space Telescope, probably through a filter that only let through the light from ionized hydrogen, or only let through the light from ionized oxygen. And we know the light from ionized hydrogen is sort of the green part of the spectrum, and the oxygen is sort of the blue part of the spectrum, and nitrogen is sort of the red part of the spectrum. And so what you do is you take those 3 images and then you color them all and you add them together, and you get what your eyes would roughly see if your eyes were that sensitive to collect that much light in one go. Otherwise, with your own eyes, you probably wouldn't actually get that much light from that object. These emission lines, though, are the main way that we identify planetary nebula now. So the Spirograph Nebula is definitely a planetary nebula because it has a lot of emission in hydrogen and oxygen and nitrogen. But it means that a lot of planetary nebula we now have are no longer round, as sort of the original name comes from. For example, we spoke about the Hourglass Nebula on this channel before. We don't understand why that's not round, but it's definitely an interesting shape to study. Same for the Spirograph Nebula as well, which is such a weird and wonderful object for us to try and explain. Yeah, okay, it's round, like a lot of planetary nebula are, because, well, stars are round, so when they poof off their layers, they come out in a nice circle as well. But then you've got this really interesting spirograph structure in there too, that we're not really sure where it came from or how it got that shape. There's one leading hypothesis at the minute, but not everybody is convinced. It's especially easy to see this spirograph structure if you just look at the image of this thing when you only let through the hydrogen ionized emission. I could stare at this image all day. It's mesmerizing. You can get lost in it. And it's this structure that people have been trying to explain for over a decade now. And we still haven't quite fully figured it out. But I'm sure a lot of people are like, it's 2020. How come we can't explain this? But of course, our observations of this thing were incredibly limited for a long time. So you can see this in a paper from the 1950s by Wilson and Aller. You can see this was an image of IC 418 taken using a telescope on the ground. And really, this thing is just a blurry round blob. You don't see any of that really cool spirograph structure, because you're looking through the atmosphere. So it wasn't until the year 2000 that the Hubble Space Telescope finally looked at this thing that we actually got enough detail to be able to see that spirograph structure. And I'm sure that just highlights people why astronomers love Hubble so much, because it just is leagues above what you can do from the ground. And you'll see on the Hubble website that actually sort of posted this image for the first time that it says that we still don't understand this object. Now, the way we observe objects in space is getting much better. We're coming up with new ways and more innovative ways of doing this all the time. One of the ways of doing that is something called an IFU, an integral field unit. And what that does, instead of just taking one spectra of one object in the sky, so just taking all the light from that object and splitting it into a spectrum and seeing what you get, what you can do instead is sort of jigsaw the object up, and you can take a fiber optic cable and just get the spectrum from that little piece of the nebula and that little piece and that little piece and make this cool mosaic of the whole object. And so in 2017, De Peter and collaborators actually managed to observe IC418 with an IFU called WIFES, the Wide Field Spectrograph, on the 2.3 meter telescope at Siding Spring Observatory in the Warren Bungles National Park. I have actually been lucky enough to go to this observatory. It is spectacular. The Southern Hemisphere sky there is just like no other. I really just wanted, while I was there, to just lay on the ground for just hours at a time and stare at the sky, but I was also really terrified of like snakes and spiders that could have got me in Australia. Everything wants to kill you there. But what this IFU gives you is sort of how much energy is found sort of radially as it moves outwards from that white dwarf star in the middle out in this planetary nebula. And the reason is because it takes a different amount of energy to ionize different atoms. So the ratio of the amount of each emission that you get tells you how much energy is in that region in the nebula. You can also, from these IFU spectras, get the velocity of the gas that's giving off that emission too, because you would expect it to be at a sharp peak, but it's actually quite broadened because some of the material is moving away from you and some of it is coming towards you, and so it's red shifted and blue shifted, and you can see that in the spectra. And so if you can work out, how broad the peaks are that you are detecting, then you can work out what speed it's moving at. If you have the speed, you can sort of get a time scale for how long it's been evolving for, because you know how far it's gone, and if you just sort of work your way back, you'll get to the time that it sort of left the middle from. But also what they found, that although the energy obviously that the white dwarf is giving off is just UV light, as that hits into the gas, it causes like a shock front. The ionization isn't instantaneous, and that shock front actually has to travel through the medium to fully ionize everything around it. And so that ionization shock front isn't actually moving at a uniform speed, because probably there's denser patches of gas here and there. But what that causes, because it's not moving at a uniform speed, is for you to get sort of instabilities that disrupt that movement through the gas and leave behind these weird little clumps of material that are glowing much brighter that you then detect when you see the emission from the ionization. And that's what gives you this weird pattern, because if you look really hard at this image and you stare at it for a really long time, hopefully you'll be able to convince yourself that actually none of those bits of structure actually connect to give you a spirograph shape. There's no actual line that you can follow to make one of those hypotrochoid shapes. Really, it's sort of a trick of the eye that sort of fills in those gaps when you see it from further away. It's actually sort of very almost textured and fluffy in a way. It reminds me of the flocculent spiral galaxies. The things that when you look at them, you're like, yes, that's a spiral galaxy. But when you ask yourself, how many spiral arms does it have? You'd be there forever trying to put a number on it, because they have this sort of weird fluffy texture to them. But that non-uniformly moving ionization shock front hypothesis from De Peter and collaborators is just that. It's just one hypothesis. It's not actually fully accepted scientific theory yet. Future observations of this object, more and more of them will hopefully tell, but who knows if we will ever understand this beautiful, weird, and wonderful creature. Oh, the drilling's restarted next door. I'm just gonna have to film and hope that that drilling noise, you can't hear it over the mic, because you can't hear the piano guy next door when he plays. So fingers crossed. But if not, if there's this weird background noise throughout the whole video, that's what it is. It's next door drilling. And an epitrochoid is when you do the same. And an And an epitrochoid, a nebula is... Oh, that noise is so annoying. Is nebula Greek or is nebula... Also what they found is that as that energy comes off the white dwarf, it obviously... Motorbike, damn you! Go away. Ruining the piece. And what they... Oh, why are you revving again? And what they found